Greetings, fellow brain enthusiasts and curious minds. Today, we're plugging into the electrifying world within your head as we delve into the dynamic dance of electric events during neuronal excitation and inhibition. We are Equation by Pharmacist Moms, and welcome to a thrilling exploration of the sparks and silences that define the symphony of our neural activity. Our brains are electric powerhouses, constantly buzzing with activity, sending signals that shape our thoughts, actions, and emotions. In this video, we're going to uncover the high-voltage events that occur when neurons fire up in excitement and when they hit the brakes to bring calm to the storm. Whether you're a neuroscience enthusiast, a student eager to untangle the mysteries, or simply someone fascinated by the inner workings of the brain, you're in for a shockingly good time. So, hit that subscribe button, join our community of neural explorers, and let's unravel the electric symphony of the mind together. In this video, we will learn 1. Electrical events during neuronal excitation, including resting membrane potential of the neuronal soma, concentration differences of ions across the neuronal somal membrane, Nernst potential, uniform distribution of electrical potential inside the soma, effective synaptic excitation on the postsynaptic membrane, excitatory postsynaptic potential, and generation of action potentials in the initial segment of the axons, leaving the neuron threshold for excitation. 2. Electrical events during neuronal inhibition, including effective inhibitory synapses on the postsynaptic membrane, inhibitory postsynaptic potential, and presynaptic inhibition. 3. Time course of postsynaptic potentials. 4. Spatial summation. 5. Temporal summation. 6. Special functions of dendrites for exciting neurons, including large spatial field of excitation of the dendrites, transmission of signals within the same neuron by electrotonic conduction, how electronic conduction is decreased in the dendrites, and summation of excitation and inhibition in dendrites. 7. Relation of state of excitation of the neuron to rate of firing. Before we dive into the pulsating world of neuronal events, don't forget to give us a thumbs up if you're ready to explore the electrifying secrets within your own brain. Now, let the electric journey begin. What are the electrical events during neuronal excitation? Let's learn. Except for quantitative differences, the electrical events in neuronal excitation that we are going to discuss apply to most neurons of the nervous system. This figure shows the soma of a spinal motor neuron, indicating a resting membrane potential of about -65 millivolts. This is somewhat less negative than the -90 millivolts found in large peripheral nerve fibers, and in skeletal muscle fibers. The lower voltage is important because it allows both positive and negative control of the degree of excitability of the neuron. That is, decreasing the voltage to a less negative value makes the membrane of the neuron more excitable, whereas increasing this voltage to a more negative value makes the neuron less excitable. This is the basis for the two modes of function of the neuron, either excitation or inhibition. This figure also shows the concentration differences across the neuronal somal membrane of the three ions that are most important for neuronal function: sodium ions, potassium ions, and chloride ions. At the top, the sodium ion concentration is shown to be high in the extracellular fluid, that is, 142 milliequivalents per liter, but low inside the neuron, that is, 14 milliequivalents per liter. This sodium concentration gradient is caused by a strong somal membrane sodium pump that continually pumps sodium out of the neuron. The figure also shows that potassium ion concentration is high inside the neuronal soma, that is 120 milliequivalents per liter, but low in the extracellular fluid, that is 4.5 milliequivalents per liter. It shows that there is a potassium pump, the other half of the sodium-potassium pump, that pumps potassium to the interior. This figure shows the chloride ion to be of high concentration in the extracellular fluid but low concentration inside the neuron. The membrane may be somewhat permeable to chloride ions, and there may be a weak chloride pump. Yet most of the reason for the low concentration of chloride ions inside the neuron is the -65 millivolts in the neuron. That is, this negative voltage repels the negatively charged chloride ions, forcing them outward through the pores until the concentration is much less inside the membrane than outside. What is Nernst potential? An electrical potential across the cell membrane can oppose movement of ions through a membrane if the potential is of proper polarity and magnitude. A potential that exactly opposes movement of an ion is called the Nernst potential for that ion. The equation for this is EMF is equal to plus minus 61 into log of concentration inside divided by concentration outside, where EMF is the Nernst potential in millivolts on the inside of the membrane. The potential will be negative for positive ions and positive for negative ions. Now, let us calculate the Nernst potential that will exactly oppose the movement of each of the three separate ions, sodium, potassium, and chloride. For the sodium concentration difference, 142 milliequivalents per liter on the exterior and 14 milliequivalents per liter on the interior, the membrane potential that will exactly oppose sodium ion movement through the sodium channels calculates to be plus 61 millivolts. However, the actual membrane potential is minus 65 millivolts, not plus 61 millivolts. Therefore, those sodium ions that leak to the interior are immediately pumped back to the exterior by the sodium pump, thus maintaining the minus 65 millivolt negative potential inside the neuron. For potassium ions, the concentration gradient is 120 milliequivalents per liter inside the neuron and 4.5 milliequivalents per liter outside. This calculates to be a Nernst potential of minus 86 millivolts inside the neuron, which is more negative than the minus 65 that actually exists. Therefore, because of the high intracellular potassium ion concentration, there is a net tendency for potassium ions to diffuse to the outside of the neuron, but this is opposed by continual pumping of these potassium ions back to the interior. Finally, the chloride ion gradient, 107 milliequivalents per liter outside and 8 milliequivalents per liter inside, yields a Nernst potential of minus 70 millivolts inside the neuron, which is only slightly more negative than the actual measured value of minus 65 millivolts. Therefore, chloride ions tend to leak very slightly to the interior of the neuron, but those few that do leak are moved back to the exterior, perhaps by an active chloride pump. Keep these three Nernst potentials in mind, and remember the direction in which the different ions tend to diffuse, because this information is important in understanding both excitation and inhibition of the neuron by synapse activation or inactivation of ion channels. How electrical potential is uniformly distributed inside the soma. The interior of the neuronal soma contains a highly conductive electrolytic solution, the intracellular fluid of the neuron. Furthermore, the diameter of the neuronal soma is large, that is, from 10 to 80 micrometers, causing almost no resistance to conduction of electric current from one part of the somal interior to another part. Therefore, any change in potential in any part of the intrasomal fluid causes an almost exactly equal change in potential at all other points inside the soma, that is, as long as the neuron is not transmitting an action potential. This is an important principle because it plays a major role in summation of signals entering the neuron from multiple sources. What is the effect of synaptic excitation on the postsynaptic membrane? Let's discuss. Figure A shows the resting neuron with an unexcited presynaptic terminal resting on its surface. The resting membrane potential everywhere in the soma is minus 65 millivolts. Figure B shows a presynaptic terminal that has secreted an excitatory transmitter into the cleft between the terminal and the neuronal somal membrane. This transmitter acts on the membrane excitatory receptor to increase the membrane's permeability to sodium. Because of the large sodium concentration gradient and large electrical negativity inside the neuron, sodium ions diffuse rapidly to the inside of the membrane. The rapid influx of positively charged sodium ions to the interior neutralizes part of the negativity of the resting membrane potential. Thus, in Figure B, the resting membrane potential has increased in the positive direction from -65 to -45 millivolts. This positive increase in voltage above the normal resting neuronal potential, that is, to a less negative value, is called the excitatory postsynaptic potential, or EPSP, because if this potential rises high enough in the positive direction, it will elicit an action potential in the postsynaptic neuron, thus exciting it. In this case, the EPSP is plus 20 millivolts, that is, 20 millivolts more positive than the resting value. However, we must issue a word of warning. Discharge of a single presynaptic terminal can never increase the neuronal potential from -65 millivolts all the way up to -45 millivolts. An increase of this magnitude requires simultaneous discharge of many terminals, about 40 to 80, for the usual anterior motor neuron at the same time or in rapid succession. This occurs by a process called summation, which we will discuss later on. How is action potential generated in the initial segment of the axon leaving the neuron? Let's discover. When the EPSP rises high enough in the positive direction, there comes a point at which this initiates an action potential in the neuron. However, the action potential does not begin adjacent to the excitatory synapses. Instead, it begins in the initial segment of the axon, where the axon leaves the neuronal soma. The main reason for this point of origin of the action potential is that the soma has relatively few voltage-gated sodium channels in its membrane, which makes it difficult for the EPSP to open the required number of sodium channels to elicit an action potential. Conversely, the membrane of the initial segment has 7 times as great a concentration of voltage-gated sodium channels, as does the soma, and, therefore, can generate an action potential with much greater ease than can the soma. The EPSP that will elicit an action potential in the axon initial segment is between plus 10 and plus 20 millivolts. This is in contrast to the plus 30 or plus 40 millivolts, or more required on the soma. Once the action potential begins, it travels peripherally along the axon, and usually also backward, over the soma. In some instances, it travels backward into the dendrites, but not into all of them, because they, like the neuronal soma, have very few voltage-gated sodium channels, and therefore frequently cannot generate action potentials at all. Thus, in Figure B, the threshold for excitation of the neuron is shown to be about -45 millivolts, which represents an EPSP of plus 20 millivolts, that is, 20 millivolts more positive than the normal resting neuronal potential of -65 millivolts. Next we will discuss electrical events during neuronal inhibition. What is the effect of inhibitory synapses on the postsynaptic membrane? Let's learn. We calculated the Nernst potential for chloride ions to be about -70 millivolts. This potential is more negative than the -65 millivolts normally present inside the resting neuronal membrane. Therefore, opening the chloride channels will allow negatively charged chloride ions to move from the extracellular fluid to the interior, which will make the interior membrane potential more negative than normal, approaching the -70 millivolt level. Opening potassium channels will allow positively charged potassium ions to move to the exterior, and this will also make the interior membrane potential more negative than usual. Thus, both chloride influx and potassium efflux increase the degree of intracellular negativity, which is called hyperpolarization. This inhibits the neuron because the membrane potential is even more negative than the normal intracellular potential. Therefore, an increase in negativity beyond the normal resting membrane potential level is called an inhibitory postsynaptic potential or IPSP. Figure C shows a neuron in an inhibited state with a more negative intraneuronal membrane potential, that is, -70 mV, caused by potassium ion efflux, chloride ion influx, or both. What is presynaptic inhibition? Let's learn. Presynaptic inhibition is caused by release of an inhibitory substance onto the outsides of the presynaptic nerve fibrils before their own endings terminate on the postsynaptic neuron. In most cases, the inhibitory transmitter substance is GABA, that is, gamma-aminobutyric acid. This has a specific effect of opening anion channels, allowing large numbers of chloride ions to diffuse into the terminal fibril. The negative charges of these ions inhibit synaptic transmission because they cancel much of the excitatory effect of the positively charged sodium ions that also enter the terminal fibrils when an action potential arrives. What is the time course of postsynaptic potential? When an excitatory synapse excites, the anterior motor neuron, the neuronal membrane, becomes highly permeable to sodium ions for 1 to 2 milliseconds. During this very short time, enough sodium ions diffuse rapidly to the interior of the postsynaptic motor neuron to increase its intraneuronal potential by a few millivolts, thus creating the excitatory postsynaptic potential, or EPSP, shown by the blue and green curves of this figure. This potential then slowly declines over the next 15 milliseconds, because this is the time required for the excess positive charges to leak out of the excited neuron and to re-establish the normal resting membrane potential. Precisely the opposite effect occurs for an IPSP, that is, the inhibitory synapse increases the permeability of the membrane to potassium or chloride ions, or both, for 1 to 2 milliseconds, and this decreases the intraneuronal potential to a more negative value than normal, thereby creating the IPSP. This potential also dies away in about 15 milliseconds. What is spatial summation? This effect of summing simultaneous postsynaptic potentials by activating multiple terminals on widely spaced areas of the neuronal membrane is called spatial summation. How spatial summation occur in neurons? Excitation of a single presynaptic terminal on the surface of a neuron almost never excites the neuron. The reason for this is that the amount of transmitter substance released by a single terminal to cause an EPSP is usually no greater than 0.5 to 1 millivolt, instead of the 10 to 20 millivolts normally required to reach threshold for excitation. However, many presynaptic terminals are usually stimulated at the same time. Even though these terminals are spread over wide areas of the neuron, their effects can still summate. That is, they can add to one another until neuronal excitation does occur. This is demonstrated in this figure. The bottom postsynaptic potential, in the figure, was caused by simultaneous stimulation of 4 synapses, the next higher potential was caused by stimulation of 8 synapses, finally, a still higher EPSP was caused by stimulation of 16 synapses. In this last instance, the firing threshold had been reached, and an action potential was generated in the axon. Each time a presynaptic terminal fire, the released transmitter substance opens the membrane channels for at most a millisecond or so. But the changed postsynaptic potential lasts up to 15 milliseconds after the synaptic membrane channels have already closed. Therefore, a second opening of the same channels can increase the postsynaptic potential to a still greater level, and the more rapid the rate of stimulation, the greater the postsynaptic potential becomes. Thus, successive discharges from a single presynaptic terminal, if they occur rapidly enough, can add to one another, that is, they can summate. This type of summation is called temporal summation. Now, we will discuss some special functions of dendrites for exciting neurons. First one is large spatial field of excitation of the dendrites. The dendrites of the anterior motor neurons often extend 500 to 1000 micrometers in all directions from the neuronal soma. And these dendrites can receive signals from a large spatial area around the motor neuron. This provides a vast opportunity for summation of signals from many separate presynaptic nerve fibers. How are signals transmitted within the same neuron by electronic conduction? Most dendrites fail to transmit action potentials because their membranes have relatively few voltage-gated sodium channels, and their thresholds for excitation are too high for action potentials to occur. Yet they do transmit electrotonic current down the dendrites to the soma. How electronic conduction is decreased in the dendrites. This figure shows the stimulation of a neuron by presynaptic terminals located on dendrites, showing, especially, decrease in membrane potential as it spreads electrotonically along dendrites toward the soma, called decremental conduction of excitatory, that is, electrotonic potentials, in the two dendrites to the left, and inhibition, that is, of dendritic excitation in the dendrite that is uppermost. A powerful effect of inhibitory synapses at the initial segment of the axon is also shown. How are excitation and inhibition summed up in dendrites? The uppermost dendrite of this figure is shown to be stimulated by both excitatory and inhibitory synapses. At the tip of the dendrite is a strong excitatory postsynaptic potential, but nearer the soma are two inhibitory synapses acting on the same dendrite. These inhibitory synapses provide a hyperpolarizing voltage that completely nullifies the excitatory effect and indeed transmits a small amount of inhibition by electrotonic conduction toward the soma. Thus, dendrites can summate excitatory and inhibitory postsynaptic potentials in the same way that the soma can. Also shown in the figure are several inhibitory synapses located directly on the axon hillock and initial axon segment. This location provides especially powerful inhibition because it has the direct effect of increasing the threshold for excitation at the very point where the action potential is normally generated. What is the relation of state of excitation of the neuron to the rate of firing? Let's learn. The excitatory state of a neuron is defined as the summated degree of excitatory drive to the neuron. If there is a higher degree of excitation than inhibition of the neuron at any given instant, then it is said that there is an excitatory state. Conversely, if there is more inhibition than excitation, then it is said that there is an inhibitory state. This figure shows responses of three types of neurons to varying levels of excitatory state. Here you can see that neuron 1 has a low threshold for excitation, whereas neuron 3 has a high threshold. But also make a note that neuron 2 has the lowest maximum frequency of discharge, whereas neuron 3 has the highest maximum frequency. And there you have it, our electrifying exploration into the pulsating world of neuronal excitation and inhibition. We hope this journey has sparked a new appreciation for the dynamic events that shape the electric symphony within our brains. If you found this exploration of electric events intriguing, don't forget to give it a thumbs up, share it with your fellow brain enthusiasts, and subscribe for more enlightening content on the electrifying intricacies of the mind. The world of neurobiology is endlessly fascinating, and there's always more to learn and discover. Thank you for plugging in and joining us on this neuroelectric journey. Your questions and enthusiasm fuel our exploration of the mesmerizing events that unfold within our heads. Keep that curiosity alive, and remember, the more we understand about these electric processes, the closer we come to understanding the essence of thought. We are Equation by Pharmacist Moms, signing off for now, but stay tuned for our upcoming videos as we continue to unravel the electrifying mysteries of the brain. Until next time, keep those neurons firing and your curiosity sparking.